First of all, I want to apologize in the beginning for all the bad puns in my slides that will be happening. When you're working with time stuff, it's hard to not make parallels to things and so on. And also, as I know when I go on these talks, after about 20 minutes, I start to drop off. So I'm going to start with telling you the important bits, and then you can drop off if you want to, and we get into the gory details. So what's happening, what I'm going to talk about, is the time changes that are coming in the 18.0 release of the Erlang distribution. We've been working on this for about 6 months now. I think the revision of the APIs you see is probably the 6th, 7th revision or something like that. It doesn't look anything like the previous revisions at all. We're quite happy with the way it is. So what we're doing is that we're deprecating the Erlang now function, because the way that this is designed is a catastrophe in scalability concerns and was never possible to make the same functionality and make it work. So we're eventually hoping to remove that completely. Instead, we're introducing Erlang monotonic time and Erlang system times, which are primitives for you to fetch time from the virtual machine. Monotonic time is a time from some point in the future that just progresses monotonically, doesn't jump anywhere. And system time is a time that's fairly close to POSIX time, the way we see it, so UTC at the moment. We've added time warp modes, which is a way to handle backwards compatibility for us, so that you can run your application either in, say, no time warps, or a single time warp, or multiple time warps. The preferred method is to run multiple time warps, but almost all applications will break if they start running with that at the moment. So the backwards compatible and the default way will be no time warps. As part of this, we've implemented scalable timers, which we will think will scale very nicely, but it's not as scalable as we would like it yet. And by 18, I don't think we have the perfect solution yet. We'll continue working on that, but at least now we have the APIs to support us to do the things we want. We've also implemented, as a side effect of this, lock-free references, so that we can create parallel references how many we want, and that solution is completely lock-free at the moment, which is really nice. So that's the summary of the talk. So now we go into the gory details. I want to start first giving talk a bit about time and what that is. So if you look at Wikipedia, you can see some quotes saying that time is what makes sure that everything is not happening at once, or time is what clocks measures, which is totally doesn't make any sense at all and isn't helpful at all. Luckily, for this talk, I'm going to focus on time measurement and the way that works, and not actually what time is there. So we have this time that's called UT1, and it's been UT0, UT2, and different things. So universal time, and that's based around how the Earth rotates around its own axis and makes sure that the sun in Greenwich in England is just above your head when you're at the right place. Unfortunately, due to tidal stresses and the way that sun revolves and solar flares and whatever, that's not really a precise unit of measurement when you want to do measurement of time. It kind of varies depending on the seasons and so on, how fast this works. So we have something called UTC, which is an acronym that doesn't mean anything. It's a mix between a British, an English acronym and a French acronym, and both of them don't translate to that specific name. And it's based on the Standard Institute seconds, so the atoms decaying and how long time that takes. And obviously, these two don't match. So that's why we have things like leap seconds being introduced into UTC. So the next one is going to happen in June, and then that specific hour there is going to have one more second. So take care to use that second wisely, as it doesn't happen that often, and it's impossible to predict when these will happen because it depends on earthquakes and tornadoes and huge storm events on the Earth and so on, so you don't know when they happen. So far, it's always been increases in time, so you've added seconds, but there is the possibility to remove seconds as well in the standard. And then we have what we normally work with in computers, POSIX times, which is kind of like UTC time, as its base is in UTC, but every day is always a specific amount of seconds. So they don't have leap seconds in POSIX. They just repeat the same second twice, or they remove 1 second when these leap seconds happen. So there's a lot of different ways to do time measurement, and when you try to communicate in between different worlds, depending on if you're an astrophysicist or if you're a computer science guy, you talk about time in different ways. The Erlang, so getting closer to the subject matter, the way that time has been managed in the Erlang virtual machine throughout time has varied. The first version of it just used what the Linux primitive or the Solaris at that time, I would imagine, get time of day, which jumps a lot when NTP comes in and tries to adjust it, it runs wrongly. The system administrator, for some reason, thinks that it's a good idea to change the time on your computer. All of these things happen to you, and it becomes quite annoying. So I don't know when, at some point we added something called, that I would like to call anyway, Erlang corrected time, which is what we're using at the moment. So what this does is that it uses the OS monotonic clock, which is kind of correct, but it's not as correct as we would like. And then from that, it tries to extrapolate and tries to adjust according to what the get time of day, so the current POSIX time of the system looks like. It is a very useful extractor in that it's almost always the correct way to do things. This almost thing, that's a problem. And it's also a problem in a scalability concern doing this, because you always have to sync the virtual machine's view of time. So the different ways that we can get time today is that we can get, just to get the same vernacular when we're talking. So we have the OS system time, which is the operating system's times of POSIX time. We have the OS monotonic time, which is a system clock that's normally on some computers anyway. It measures the CPU cycles. Could be the monotonic time, for instance. And we have the Erlang corrected time. And now that we have the introduction, we'll get a summary of what I'm going to talk about. So we have a brief history of time. We're going to go through how time works today in the Erlang virtual machine, how it will work in the future. We're going to look at timers, how they work today, and how they're going to work in the future. So some of the properties that are nice about the current Erlang corrected time is that it never jumps backwards or forwards. It always progresses forward at a steady pace. It never differs in speed by more than 1% of the OS monotonic clock. So it always is either 1% slower, 1% faster than the OS monotonic clock. And it attempts to be as close as possible to the OS system time, so POSIX time. Now and the basic algorithm to figure this out is something according to these lines. We get the monotonic time, and if it's time to check sync, we get time of day, which is done about every second. We check that. And then we either increase the speed, decrease the speed, or start using the same speed again if we're caught up. The basic problem with this model is that what if system time jumps very far? So in our embedded devices, some of them that are pressed in the factory, they start in 1970. And then they get NTP contact when the Erlang virtual machine has been up and running for a while. So it takes quite a while for the Erlang virtual machine to recover. And it's and during this time, unfortunately, since when you call Erlang now, for instance, you will read this kind of time. So you will see even though your POSIX time says something like 2015, your Erlang now will say 1971, 1972, and so on, until you catch up, which is sometime in the future, when your software might be running or not. But that's kind of a problem. But the real issue is when you come to relative time, so when you're setting timers. So when you have external protocols that are trying to work with this, so if you, for instance, are doing SIP transformations, then you have timeout saying, OK, after one minute, I need to do a retransmission of this protocol, and then after 5 minutes, I need to do a reset up and whatnot if you lose connections. And that time, then, is 1% shorter on all of these machines that are running this. And this is a real issue when we're working with these things. So that's not good. And that's one of the problems that we set out to solve when we did this things. This is actually an initial problem that triggered the entire rewrite. And then all of the parallelism things just happened to pile on as we wanted to make a good API for all of it. And getting to Erlang now, and the reasons why we removed that is because of the things that you get out of Erlang now. At the moment, you get a unique value that's always increasing, and it's kind of POSIX time. So it's kind of close to POSIX time. And because of these different things, many users have been forced to use like OS timestamp instead to get the current operating system's view of time. So it's a terrible broken piece of things, and we've been wondering a long time how to change it. So how did we change it? So we're introducing something that's called the Erlang monotonic time. So we're getting rid of Erlang corrected time, kind of, and we're introducing something that's called the Erlang monotonic time. The Erlang monotonic time is very, very similar to the way that the OS monotonic time works. The only difference is that it's corrected by NTP. So if you have some kind of hardware where the internal clock is not very synced with the way real time works, the Erlang monotonic time will try to sync up with that. And the resolution and accuracy of the Erlang monotonic time is very system specific. You will see huge differences in different systems in this time, and there are quite some APIs to work with that. And we have also introduced something that we call Erlang system time, which then is a POSIX approximation of what time is, and that this time is based off the Erlang monotonic time, and we have a offset that you add to it so that you can say that, okay, you take the monotonic time and you add a time offset to it, and then you get the system time at the moment. Now this time offset can change or it cannot change depending on how you configure your system. So just a basic look at the APIs. We have Erlang monotonic time like this. It returns an integer for you. And it's some time value from some point in the past or the future that we measure from. We have a new API also called Erlang time offset that returns an integer. So you add these two to get some kind of the Erlang system time. And if you want to, so this time offset and the monotonic time, as you might notice, it says that it returns in native time units, which is nanoseconds, microseconds. It might be CPU cycles. For instance, on Windows, it's CPU cycles. So if you have a 4.9 gigahertz or something, it's the amount of CPU cycles. So it's very difficult to get an actual value out of it. On Linux, it's nanoseconds. On OS X, it's microseconds, and a lot of different variants. So you use this function to convert the time. So you get the monotonic time, and then you send in time from unit to unit. So you can say native to, I don't know, microseconds, and you get it in a microsecond resolution in there. The reason why we don't give you a standardized value from the beginning, because we can't really know which resolution you want to have or which is expected of us. And we wanted to build an API that didn't limit us. We had a lot of thoughts saying that, okay, so yeah, nanoseconds should be all right. But what if the computer in the future needs picoseconds to work with the resolution? So we wanted to design something that would be future-proof, and this is what we came up with there. There's also a convenience API for Erlang system time, which is basically just calling together monotonic time and time offsets. So using these on my Mac here, we get Erlang monotonic time. You get some kind of value up there, and you get a time offset of 0, and you add them up, and you obviously get the same thing. You convert from native to microseconds, and we can see there that actually the native unit on my Mac was microseconds. So quite convenient there. And then you can convert it to your normal now tuple if you want to, and then use calendar now to local time, and you can see the time when I wrote my slides. On my Linux Ubuntu machine, it returns negative something huge, this monotonic time. And then we have a time offset that sets it correct again, and we add it up, and we get this figure that's kind of the same. The reason for the difference here is that we want to have a predictability in the timing APIs, in the amount of data they build on the heap as they are executed. Before, it's always been, when you call Erlang now, you get the 3 tuple with 3 small integers in them. So you will always build 3 words of heap data. We want to keep it predictable so that after 20 years, all of a sudden, you don't start to create twice as much garbage on the heap if you're using these APIs as much as possible. So by placing this point of monotonic time in the future, we can make sure that if your system runs for, 256 years, then we start building big nums. Before that, we always used smalls on this Linux machine, while on the Mac that used microseconds, that doesn't happen as often because this uses nanoseconds. Then we can use a more human-readable way of working with it. So it all depends on how long your system are going to be up and running. So predictability is very important. And then you convert it from native to microseconds, and we cut out the last zeros, and so. And this also has the nice effect of making sure, since it's two quite common operating systems, it really makes sure that you use the APIs correctly and don't take any shortcuts with using them. So the different time units that you can use to send into this conversion API is seconds, milliseconds, microseconds, and you can give an arbitrary integer. So if you want to have it in the 1024 resolution, you can give 1024, and it will give whatever binary unit of time that you wanted to have it to. There's a bunch of convenience functions that you can use, like monotonic time, time offset, and system time all take a second argument. That's the unit that you want to return. So if you say monotonic time microseconds, it will return microseconds for you. But know that this is a more expensive operation and might build more things on the heap and so on. So the basic APIs are there for performance, and then you can use these ones for convenience. There's also an Erlang timestamp that gives you the familiar 3-tuple of time for you to use in all the APIs, so you don't have to rewrite your code. We're also adding a OS system time that returns this integer rather than returning the 3-tuple from the OS module if you want to get the OS POSIX time at the moment. OK. So when we were talking about now, we were talking both about time and about the uniqueness and the monotonic increasing values. So we didn't want to create a new API where we had to bundle all of that information together again. So we've created a new function. So Erlang timestamp is, of course, what you use to get the 3-tuple of time, as similar to now as possible. And then we have a new API called Erlang unique integer, which you can give a list of arguments saying either positive, monotonic, or both, and you give it, and then you get a integer value. And depending on your needs, you will use different variants here. If you want to have a monotonically increasing in the system, that requires a global lock. If you don't need a monotonically increasing value, you just need a unique integer for some reason, then you can just skip the parameters, and then you will get a integer that is not locked. So it's generated on a per scheduler basis, so you don't need any locking at all to generate that. So take care when you use these things and work with them. When we're talking about uniqueness, there's another data type that comes to mind, and that's the reference. And you might wonder, why don't we use the reference to do these things rather than using the integer? Let's see. We don't use it for two reasons. The first reason is that we want to be able to write these things to a file and then read them back up again. Writing something like in an Erlang term format and doing file consultant and having references in there is not a very good idea. So we wanted to have integers in there, and we found places in the OTP code specifically where we wanted to have this behavior in order to be backwards compatible in the way that we were using Erlang now at the moment. And one other thing to remember is that references are only guarantee uniqueness. They do not guarantee any order. At the moment, in the current virtual machine, they do guarantee order, but in 18 they will not anymore. So it will only guarantee uniqueness at that point. I'll get back to that a bit more later on. So if you're reading the documentation of how this works, there's quite a big section about time warp modes. And the time warp modes is an unfortunate side effect of that we need to be backwards compatible with these changes. And we've been thinking a lot about how to make that possible and how to make old systems that have been running forever be able to use our new APIs to get scalable time without having to rewrite large amounts of their code. So what we come up with is what we call time warp modes. So it's different ways that you want time to warp in your emulator as you run them. And the time warp modes control the way that Erlang time offset behaves, and also the way that Erlang monotonic time behaves. And specifically, it changes the behavior of when your POSIX time jumps far, and by far I think it's more than 5 milliseconds. So if it jumps by more than 5 milliseconds, that's a far jump. And if it jumps less, it's a small jump, and then we just adjust time a little bit. So starting with the first mode, which is the default mode, and it's the backwards compatible mode. So in here we have time offset. It remains constant. It will never change. You don't get any time jumps, just as it works today. And we have the Erlang monotonic time is trying to compensate for how much your time has jumped. So if it's jumped 1 year into the future, Erlang monotonic time will run 1% faster for 100 years to catch up. And this is the backwards compatible way. So if you're starting up the 18.0 emulator, this is the mode that you will get, and that's the way it's always worked, which is not the right way to do it. We also have a single time warp. So this is for applications that want to be able to use the new time APIs, but are not really there for using, converting their entire application. So what you can do is that you boot up in a specific mode, and then you only run on the OS monotonic time. So the Erlang monotonic time and the OS monotonic time will be aligned and work as one. And then at a certain point, when you know that, OK, now I've gotten connection with my NTP server and my time should be kind of OK, you say, now I want to do a jump. So the time offset does one jump, and after that it behaves just the same way as in the no time warp mode. This is for you so that you can start up a small core of your application first that just takes care to measure that, OK, now my time is correct. And then you set the time and you do a warp, and then you start the rest of your application that is not converted to use the new primitives yet. It all depends on how big and how much of effort it takes for you to convert the application. And then we have the multi-time warp mode, which is the recommended mode. And this is probably the one that's going to be default in the future. How far into the future that is, we don't really know. And what happens here is that monotonic time will be constant. It will be an NTP-adjusted monotonic time. The time offset will jump backwards and forwards on its own will, depending on how the POSIX time of your computer works. You can monitor when these events happen by doing Erlang monitor time offset on the clock service. And then you will get messages to say, now time jumped to this point, or actually it doesn't say where it jumped. It just says time jumped, and then you will have to figure out where it jumped to. This is good if you're, for instance, building a cron tab or similar in your system, things that work with absolute time. And this is the preferred way to run things. And it's the most, one of the good things about this is the most scalable and most performant way to run your application. This is the way you get the most performance out of your system. All of the other things have to do extra computations, extra locking in order to manage to get this behavior. This behavior is the one that you won't get the most scalability out of. So if you want to make sure that you don't get any contention on locks and whatnot, you want to start to use this mode. So that's that about time. So let's talk about relative time. Specifically, the only relative time we really have in Erlang is timers and the way that we measure these things. At the moment, that's supposed to be, say, corrected time. So at the moment, it's based on Erlang corrected time. And as I mentioned before, you have this problem with timers triggering either too early or too fast if you compare it to an external source in the system. The guarantees that we have is that a timer is not allowed to trigger before the timeout. We have timers that are either associated with a message, so the timer biffs like send after or something like that, or we have something that's not part of a message, we have receive after timeout. And the timer module, despite its name, has nothing to do with timers in Erlang. The timer module is an Erlang implementation of how to manage timers there. So these, when we talk about these things internally, we call them BIF timers because they are, and that's Erlang timers, the timer module. So the APIs that you use is send after, start timer, cancel timer, or received after milliseconds for that. The timers that have a message associated with them are put into a hash table first. So you get a reference for your timer, and the message that should be sent to whatever process is put into a hash table that at the moment is protected by a large mutex. So normally when you have a system that gets maybe 12, 16 cores and you have a lot of things running on it, this is the bottleneck that you will be hitting. You will be clashing on this mutex all the time. Now, we've been quite sure that we could eliminate this mutex for quite some time. The problem is that beneath this, we have a timer wheel implementation that, again, is protected by a global mutex. So even if we solved the one with the BIF timers, we would have fallen back on the timer wheel mutex and getting that in there instead. So that's why we haven't solved that yet, or until now, I should say. And then the receive after obviously only goes directly into the timer wheel. It's not part of this hash table. So I thought I'd spend some time just explaining a bit about how the timer wheel works. So the timer wheel is a big C array. I think it's something like 65,539 elements or something like that, whatever 2 to the power it is, with slots. And you put a timer, you have a linked list of timers and a counter for each timer to say how many times in the wheel it should survive. So since we have something like 65,000 slots, and we have a millisecond resolution, it takes about 65 seconds for an entire loop of the wheel to go around. And when we do timers, we move the timing once, let's see, move it forward, and we trigger the timer that has 0, and we decrement the value. So on the slide before we had 2 and 0 there. So we trigger the timer at 0, and we decrement it by 1, the other one. So we loop through all of them in there. And then as time goes on, you can see we do a jump in between here, so we sleep for that amount of time if there's not any other Erlang-related work that has to be done, like a process executing or something. So we sleep until the next timer, we trigger that one. We decrement that one because it was net 0. And then we go through all of the things and sleep. And then we're back at the beginning and keep on going and going and going. So that's why it's called a wheel, because we go around the array, and then we start from the beginning and go around and round, around, around. This is very useful data structure to work with timers. So how will they work in the future? So it will, instead of being based on the Erlang corrected time, we base it on the Erlang monotonic time, which will mean that time jumps and so on won't affect us unless we're running into no time warp mode, because then, of course, it's the Erlang monotonic time that's adjusted by a 1% speed increase, so then we will have the same problem as all. But if we run in a multi-time warp mode, then it should work fine. And we have one timer wheel per scheduler. At the moment, each of these timer wheels is guarded by a mutex, so any scheduler can do operations in any of them. Eventually, we will most probably remove this and do it by asynchronous message passing instead. And at the moment, the BIF time, so the message timers implementation has been moved into pure Erlang. So there's no C code at the moment with that. So we have one timer process per scheduler that's running that. So that's an Erlang process. And it's not bound to any scheduler or anything like that. It's just that we have one process per scheduler that's started. When we get timers working like this, one of the consequences is that a process will have timers in multiple wheels. So if we say that green is one process and yellow is one process, they all have timers in different wheels. And because of time being local to each scheduler, the order that you put timers into the wheel might not be the order that they are triggered. Remember, the only guarantee we give about timers is that a timer should not be triggered before the time it happens. It doesn't say anything about the order which timers are put in or how long afterwards they might be triggered. This order thing is already present today in the emulator. You have to insert a lot of timers in the same millisecond in order to see it, but it's there today. So if you put If you do like a list sequence and then put a lot of timers into the timer wheel, the message order that you get them in will not be the same as you put them in. And this will become more evident with this solution, with this new implementation, as you will have larger latencies in between the different wheels. But that behavior has always been like that, and it will always be like that. And it's a huge benefit when we're doing the scalability implementations. I was talking about reference as well. So when we were working with this, we realized that timers, and specifically the timers with data attached to them, they return some kind of reference when they are there. So in order to make the timer implementation scalable, we wanted to embed the scheduler data into the reference. So a normal reference is about 85 bits long. And if you create one every nanosecond, it will wrap in 160 million years. So for the foreseeable future, we are OK on that front. In 18, we will take 18 of those bits and make it into a scheduler-specific part. So now instead of 160 million years, it will wrap in 584 years. We thought this was an OK compromise. If you have systems that will run for longer, let us know, and maybe we'll give you another bit, and you can run for 1,000 and something years. The nice thing about this is that you can see which scheduler has created a reference. So we can do a reverse lookup. So when you, for instance, want to cancel a timer, we can say that, oh, but we know that this scheduler created this reference with this timer, so we know which scheduler the specific timer process we should send the cancellation message to. So we don't get any conflict at all when we're doing this. One of the bad things, or badish things, is that references can no longer be used to order events. So if you take a reference and then take another reference and you compare those, they might compare so that the one that is taken afterwards is smaller than the one taken before. And that's a change that's going to happen in the virtual machine. That's we don't know, but we haven't found any people using references in that way yet. I'm sure there are. But that was something we needed to do in order to get this. Yes, Jim?
Does it impact the performance improvement on Gen servers, selective receive?
Yes, it will become more scalable because you create references much without taking any, because at the moment when you create the reference, you take a global mutex and you increment the value and then you release the mutex. With this, you just have to bump a pointer in the local scheduler data, and that's it for making a reference. So it will become much more scalable.
I meant the hack for the synchronous callback.
Yeah, it's still fine.
It works the same.
Yeah, it's still fine because for that to work, it needs uniqueness. It doesn't need the order. Yep. OK. So as I said, the timers with a message attached to them is a pure Erlang implementation at the moment. It uses this reference trick to look up the process. It has one ordered set edge table for timers, so that we just take the first one of the ordered set and put that into the timer wheel. And then when we get either we get a message saying we need to insert a new timer or cancel our timer, or we wait until that time in the receive after. And we have one order and one set for fast deletion, so that we can just get a reference, do an index lookup into a hash table, get that timer, and delete it quickly. Unfortunately, that implementation is not really as fast as we would like it to be at the moment. So most probably by the release of 18, we will have moved it back into C. But for the release candidate that's out at the moment, it's in pure Erlang. Our measurements from internally and at the different Ericsson customers, we've seen too much. I don't know what too much is in its constant, but they have quite strict requirements, and so I would imagine that 0.1% overhead would be too much for them. So we'll see what happens there. Either we'll optimize Erlang or we'll put it into C. So to sum up, we deprecated Erlang now. We have a new scalable API. We have time warp modes to handle backwards compatibility. We have somewhat more scalable timers, but not perfectly scalable timers yet. And we have lock-free reference creation. Questions? That will depend on the operating system you're running on, unfortunately. So there's no clear way. I think we have decided that sleeping or hibernating your PC, you will get, I think on Linux we use the get clock, monotonic clock, which I believe does jump when you go to sleep. I can't remember, but it will depend on what operating system you're running on. I'm pretty sure. I don't have the exact answer, unfortunately, on how it will work. It's something we've thought about, but I can't remember the arguments on the different sides. Yeah.
First question is, how did you come about like 500 in 4 years? Like, what was the decision around 500 before? Why not 600? Why not 500? Like, that's the best question.
With that number, it's just what happens when you take the number of whatever time unit it was and do it 2 to the power 64. So it's the, I guess it's the amount, from today, it's the amount of nanoseconds that you get when you do 2 to the power 64.
Then the second question is, you said you assign timer processes to schedulers. Like, how do you do that?
They are registered by a name, I believe, and then you create an atom, and then you send a message to it.
Yeah. So how do you ensure that like it doesn't go to more than one, like more than one timer process doesn't go to more than one schedule? Like you don't have multiple processes going to the same schedule.
We don't. You will get that scenario as you generate it. It will be, you have one, if you have a scenario where you're only running code on one scheduler because of the work migration has only migrated all the processes to one scheduler as you're running on what 1/8 of the load that the system can comply, then all of them will be put in the same process. But at that point, you don't have a scalability issue because you're running on 1/8 of the power. But if you're running on 100% of the things, then all of the schedulers will be busy generating timers and being put into the different parallel processes. So that should be fine. So
Okay, just for clarification, I think this might be out of scope you talk, but all of these changes, will these changes affect any semantic change of the calendar module, like the date and time stuff?
no.
No.
Do you plan to add time coordination between nodes, like sharing with?
No. No, we've thought about it to do it, but it was way too much work to do that. And I think we kind of decided that we will not handle that at the level that we're working in a way. If we write high-level constructs, do that later on top of these primitives, that might be something. But we're not going to do any low-level primitives for doing that at the moment anyway. Possible, yes. Probably not. I mean, if you have the scenario where you're, for instance, running a long-running NIF in one of the schedulers that you're not supposed to be, you will be blocking all of the timers within that scheduler for that amount of time that you're running. So if you're running it for 10 seconds, that all timers in that wheel will be delayed for 10 seconds until, boom, all of a sudden we get back to running again. But by now, I hope everybody has learned that they shouldn't do that. So we hope that that won't happen. We'll see.
Any other questions?
Is there any way to see the difference between the system time and the actual system time? Is there any way to get bounds on that, even if it's just statistical?
To see how much it will differ.
Yeah.
No, not really. I don't know as such. No. Yeah, how much they differ in that way? Not a lot normally, but we've had some wonky hardware where it's been very different. So we're trying to compensate for that. I haven't been involved with those measurements, so I don't know the answer, the specific answer. It's some other guys that did that. Mm.
question's completely unrelated. Process or scheduler binding in Linux is amazing for getting high throughput cases on the run VM, and it doesn't happen at all on OS 10 because this new kernel is different. Is there any work you guys have been doing, like I mentioned you're not doing a lot of kernel work on that side of the fence, it's all on the Vue side, so it's not supported on the kernel that you're relying on top of, you're just kind of going
It does. It can't be done. On the OS 10 kernel, we've looked for the primitives and it's impossible. They don't allow it to do that kind of binding. It's only the Linux kernel that allows you to do that. My information is about 4 years out of date on this, but the last time I checked with these things, it's not possible.
Who deploys it?
Yeah, who does? Yeah.
Cool.
Okay. Thank you.